Absolutely. Good afternoon, everyone. Welcome to PCS seminar. Today's speaker is Masayuki Kimura in Setsunan University. The scientific host, Juan Aguilera, will introduce him.
Well, it's for me a pleasure to introduce Professor Masayuki Kimura from Setsunan University, because we have been working together and become friends from long ago, I think from 2016 in a conference in Ufa, Russia, and then a conference in Kyoto. I've been very often at Osaka University, which is maybe half an hour far away by train from Kyoto. About the speaker, he did his bachelor and master and PhD in Kyoto University, which is, I think, perhaps the first university in Japan. Am I right?
Yeah,
I think so. Maybe after Tokyo and the third maybe Osaka. He's PhD in electrical engineering, also about intrinsic localized modes. And then he has different positions in Kyoto University, and recently he changed, 2 years ago, he changed to Setsunan University in Osaka, also very close to Kyoto. Basically, I think he's living still in Kyoto. He has been working in engineering about localized modes, partly in theory. He's a great numerical analyst, and also doing system models. We could really observe this phenomena which we observe in lattices. Also, we have had the pleasure to organize in March together, in March this year, the second Japanese-Spanish symposium on localization.
Next year. This year doesn't work. Next year.
2024. We did.
Oh,
we just did.
Sorry.
We just organized the second Japanese-Spanish symposium on localization in lattices and waves. And his talk, it is, just as I said, his topic, it is experimental work on localized vibrations in nonlinear lattices. Thank you.
Thank you very much. Thank you very much for inviting me, Sergey, and our staff. And also, thank you very much for changing the time from 4 p.m. to 5 p.m. because of my tight schedule. But it was okay. Taxi driver is one, so I can hear before 30 minutes. Okay, so now my name is Masayuki Kimura from Setsunan University. It is a private university, not so a big university, but okay. So then today I'm going to talk about experimental works on localized mode, localized excitation in experimental system, like a nonlinear lattices. So first of all, I'd like to introduce my university and the city. Here, this is the map of Japan and Korea. Here, this is the where we are, and also the Setsunan University is between Kyoto and Osaka. And here, this is an enlarged map, and Setsunan University has two campuses. One is Hirakata, it's near Kyoto, and the other one is main campus called Niyagawa campus. This is a picture of Niyagawa campus. My office is in this building. Okay, so then this is a basic information on our university. 1975 Setsunan University was founded. And now we have 9 departments in science and engineering and international study, including foreign studies or something like this. And we have about 400 faculty staff and 10,000 undergraduate students, and just for 114 graduate students. I mean, our university is not so good at research, but also for the basic education for the undergraduate students. So, okay. So then let's move on to my main topics. Now, first, this is the introduction of my talk. I guess almost all guys know about the basics of localization, but I will introduce what is localized mode. This is a movie of localized mode, which is called site-centered mode or Sievers-Takeda mode. This atom mass oscillate with large amplitude. The other is not so large, and it keeps the position. The center of oscillation keeps here and doesn't move. And this one is another symmetric mode. It's called bond-centered mode or page mode. This is called intrinsic localized mode, ILM, or discrete breathers, EB. This one, discrete breathers or intrinsic localized modes are suggested to exist in realistic material like carbon graphene or carbon nanotubes or the potassium layer in mica muscovite. This is research with one article. In this such system, intrinsic localized mode can be moved, and also that for this. Okay, so then my previous research, we investigated 1D FPU beta chain. This is sorry. Okay, this is the traditional model, and we introduce another dimension to dimension. This means FPU chain can be deformed like this because of the additional dimension exists like this.
So this is in 2D or in 3D?
2D, but we did some discussion on 3D. But,
but in this model, it's 2D.
2D, yes. And here, this is the new type of breather. This is the lattice axis, but the oscillation is perpendicular to this lattice axis. Also, another important thing is its instability because of the additional dimension. I mean, this is kind of backplane instability. Yeah, P mode is usually stable in beta FPU chain if beta is positive, but in this case, it becomes unstable. Okay, so then
Sorry, what are the boundary conditions here?
This is periodic boundary conditions. It's great. So then, in a motivation of my work is how to manipulate or control static ILM. That I mean, position of the localization. We can how to change the position, how to manipulate one. And another one is how to create moving breathers. Because of my research focus on the application of localized oscillation in engineering field. So then we need control and creation, something like engineering from engineering viewpoint. And also the characteristics of moving ILM is my main interest. So in this presentation, I focus on the experimental work on static breathers, also the moving breathers. Okay.
Sorry, may I ask you one question? The previous slide about this instability. You said that some additional dimension cause this instability. Is it necessary there's some additional force along this additional dimension, or you don't need any additional force to see this instability? What is that?
You don't need any additional force because here this equation of solution is completely same as in the rigid one, because the initial oscillation is constrained to the lattice axis. But if you put some small noises, the noise makes noise. Because of the noise, it become an unstable like this.
Thanks.
It makes sense. Okay. So it's just small. It's like a billiard. It's if you change a little bit and change become large and large. It's like a collision small.
But in this case, you actually start from the whatever it's called, this longitudinal P mode, and you say it's unstable in 2 dimensions, right? As you showed me.
Yeah.
But in the left, you show is a so-called transverse mode.
Yes.
With this ST was centered on the side. So what happens if you can you also construct a transverse P mode which is stable?
So I'm sorry, I'm almost forgot, but this one is a bit different from the longitudinal one.
Well, it's transverse, right?
Yes, transverse.
But it's centered on a side, and you say it's stable, right? That one is stable.
Yeah, I think so, but sorry, I have to remember the papers.
I can talk then.
Okay. All right. So then let's move on to the work. Here's the famous experimental work in our research field. This is fabricated by Mike Russell, who is a really famous researcher. He observed shockwave in a localized mode. This is the result. And here you can see small magnets are put on the steel plate, and pendulum is arranged this straight line, and it can move not only this direction but also that direction, and it can mimic the motion of the atom in on the atomic lattice. So this is this work affects my research. So here this is another experimental work. This is small one is attached to this rigid, but it can be. This is a spring and also the permanent magnet, and it can be magnetic interaction between them. This is another one. This is just a pendulum, and it is the top view, and you can this bar it was oscillate with some frequency, and you can see the moving localized oscillation.
And to take into account the damping effect.
Sorry.
To consider the magnetic damping
Damping.
in the model.
Yes, in my experimental model, we have to consider the damping because to represent the experimental phenomena in my computer. But not to, okay. So then here's another model. This is in the mass and spring, and this is fabricated by him. He is my colleague in the same university, and this is an example of creating and moving discrete breather from here. You can see moving breather graded up this edge and go like this. This is the numerical simulation. No, this is the experimental observation. You can see this clearly. The breather goes.
So this breather looked like it's a longitudinal.
Yes.
So then it doesn't become unstable?
Yes, because this spring is really strong with respect to this perpendicular transverse displacement.
What about this direction?
Yes, only this one cannot deform freely to this motion, because only this longitudinal motion can be occurred in the system. It is a kind of a one of his work to prevent making like a not necessary motion. Yeah, he really wants to mimic one rigid line. So then
So one dimensional.
yes, yes. So then also this one. So you can see V shape here. So this may be the pendulum only oscillate like this, not like that. Thank you. Okay, so then let's move on to my system. My first experimental system is shown here. This system has been fabricated in my PhD when I was PhD student. Here, this is a rigid support, and this voice coil motor makes an oscillation. And each cantilever connected by elastic rod, and this is electromagnet, and permanent magnet is attached at the tip of the cantilever, and then this has nonlinear on-site potential. Okay, so then here, this is a photo, and not so many degree of freedoms, but it has 8 or maybe 10 or 8 oscillators is connected by this line, and each oscillator connected by almost a linear coupling constant, and also it can be, I'm sorry. Okay, this is electromagnet, and this is a voice coil motor. And this is basic characteristics of each oscillator. This is the equation of motion. F is the on-site potential induced by a magnetic force. And A cos omega t is created by voice coil motor. And C is the connection, linear connection between each cantilever. And this is a typical parameters for this equation, and this is the frequency setting. You can see the hysteresis characteristics with respect to the frequency of the exciter, and then upscan and downscan shows a different curve, and in between this edge and that edge, you can obtain 2 stable states. One is large amplitude, the other one is small amplitude. This is the condition we can observe the localized solution like this. Okay, so then in this experiment, we tune the frequency at 36.1 hertz. Okay, here, this is an experimental results. This is the ground state, no ILM state, but of course, this voice coil motor oscillation. Okay.
Yeah, in the previous slide. So in this system of equations, in total, how many discrete breathers do we have?
I guess
Only 2, as you were showing there?
no. We have 8
per each side.
Yes, each side. Yes.
So then those 2 that you are showing, what does that correspond to?
Oh, sorry, but
In this scan, when you're doing frequency scan,
Oh, I see.
You
Yeah.
have 2 distinct things. What are these 2 different things?
What is the blue and the red curve? What are they?
Okay. Okay. This is an experiment for one cantilever. You know, I mean, how can I say?
So the others are still interacting with it, or you just have one?
Yes, just one.
The others are fixed or are removed?
Fixed.
Okay.
Fixed.
So this, okay, and then you just look
Yeah.
at the,
So then you observe the
with the driving,
Yeah.
you look, okay.
Change the omega of this term, and yeah, this is the 0 and.
So blue means you scan up and red
Yes.
means scan down with some hysteresis the next.
Yeah.
Because these are magnetic systems.
Yeah, dissipative especially.
Okay, so then ground state, and you can excite one breather here, but another parameter exactly the same as in the previous slide, and the other one is here. Maybe this small oscillation because of maybe some impurity or defects of the experimental system, and the other side is.
So the resonance frequency was about 40 hertz, right? This is where
No.
you try to excite. Can you show this hysteresis? Yes.
Yes.
So at which frequency do you then operate? At the black one or?
Yes.
At which When you look at these localized excitations, which frequency do you choose?
Here, between them.
The black one, yeah? No. In the next slide, you showed the breather solution state. So for that, you also drive the system at a certain frequency.
Yeah, that's
And so what is the frequency? 36.
Yeah.
So
the same.
right. So now then my next question is, what is the spectrum of the linear phonon-like excitation? So
Yes, phonon band is about 35.1 hertz, and yeah, this is around here. And
to the left.
yeah, and system is small linear coupling constant, and band is so narrow. And this one, this electromagnet makes attractive force. So then you magnetic interaction between permanent magnet and electromagnet makes attractive force. So then the natural frequency shifts to the high because of the.
It's a hard nonlinearity.
Yes. Hard, no, soft nonlinearity because yes, here you can see this one curve. So the nonlinearity is soft, but the natural frequency should be shifted to high because of the magnetic interaction, the force to the how can I say that? It makes a okay. I have another. Sorry. Okay, so this is a model of my system. The magnetic charge is a really rough approximation, but it works fine. And then this is the force curve with respect to the displacements, and this is how the potential changes by magnetic force. Here, this is how to change the potential. Because of attractive force, it makes more narrow, steep, but this sharp one becomes much more shallow, and then it makes soft nonlinearity. Yeah, this is a force curve, a response curve, skeleton curve with respect to the frequency and amplitude. This is this skeleton curve is drawn by simulation on the conservative system.
But then if you're in your picture with these frequencies, the phonon band was to the left.
Yes.
And you have soft nonlinearity, you would expect states below it, but you say you drive them at frequencies above the phonon band. How does that?
Yes, that's right. Yeah. So that's why so yeah, here this is the bottom of the phonon band.
Right.
And if you choose the current around here, maybe this is impossible to make a discrete breather. But if you increase the amount of current of the electromagnet, it makes it's enough separated by linear band and here. Okay, I misunderstood your question because then changing the current of electromagnet also changes the band. But yes, so then sorry. If you choose this value for the electromagnet, then this is the bottom of the phonon band.
Oh, okay. You shift the phonon band.
Yes,
Shift the phonon band.
Yes. Sorry for misunderstood.
Because of the steepening of the potential, so you push it up.
Yes. Okay. This is moving. Now I side. This is really analog. But yeah, you can see difficult to see, but this is the localized state. Yeah. And you can destroy easily. And the other side. And sometimes it is difficult to this side as the okay. This is the comparison between experiments and numerical simulation. This seems very nice. Okay, so maybe I can skip this one because this is okay, but this is important result for my research. This is a demonstration of manipulation by using imprinting. This is the first state. Here, number 5, localized state is here, and now the current of number 4 electromagnet changes at this line. Okay, from 24 milliampere to the 11.5 milliampere. It starts to move to the 4, and then if you increase the amount of current to the original amount, the manipulation has been completed. Okay, you can see the position is shifted from 5 to 4. Okay, it is first reported by Masayuki Sato, Kanazawa University. He tried to IR laser, and they can track the manipulation, also reversible manipulation. Here, this is another example of manipulation by using imprinting. Okay, here this is the how numerical simulation and also the basin of attraction. And here this is the unstable P mode and stable ST mode, and trajectory here. This is okay. And now, yeah, this is current change. Okay, that's okay. It is not experimental work, but it's result of it. Okay, let's move on to another one. This system has nonlinearity between neighboring oscillator cantilevers. This is not elastic world, but it has magnet. So then it has actually, this is what the system looks like. Okay, cantilever and magnet, permanent magnet, and support. The system is almost the same as in the previous one. Okay, so this is the modification, but also almost the same, but only the coupling arm is different from previous one. Okay, here, sorry. Yes, this and so the movie continue. I see this is the on-site station, and in this system, center. All right. Then recently we have.
Sorry.
Sure.
I didn't understand. Maybe in the previous experimental data that you showed, where you were showing the current and the oscillations, I thought what you did was you first excite one of these cantilevers, then you change the current, and then what happens is that this oscillation moves from one side to another side.
Yes, yes.
But in these videos, you are always disturbing them with hand.
Yes. This one is another one, and this movie shows both on-site and inter-site mode are stable. This is because of the maybe the nonlinear interaction. It makes really complicated results. Again, then now move on to the recent work on 2 degree of freedom oscillators array. Okay, here, this is some prototype a very prototype of our system. Yeah, you can see permanent magnet and elastic rod is attached here. Then this is almost the same as in the Mike's work. And here, this is the new one. Magnet gives nonlinear interaction between to each rod, and this is shaper makes an excitation. The ion plate is fixed support. Okay, this is the movie. This is the high-speed camera, and you can see wave traveling wave from here to there. It is the excited of traveling wave because of the excitation frequencies inside phonon band. And this is a result when the frequency tuned near the above the top of the phonon band. You can see the zigzag motion. You can see zigzag motion in the okay. And if you choose the frequency above the phonon band, you can see moving breather from here to there. You can see this is maybe the center of a moving breather, and it is really difficult to see, but okay, this one is much more clear. Okay, one is now traveling here. They are long. I guess because of the strong damping, so then the amplitude becomes small and small when they move from here to there. Okay, this is the top view of the traveling mode. And yeah, this is an excitation edge, and you can see this is very strong, strange motion, but they can move at constant speed. Yes, here is no, this one is center is not here. No, this is very difficult to see, but this one is now localized motion. Propagate like this. Okay. The phenomena is very similar, but there has a transverse motion. And here, this is the numerical simulation, and exciter is here, and you can see the traveling mode excited from here and goes to this direction. And okay, yeah, this panel shows the Y motion, and if you choose the amplitude of excitation, exciter relatively small, you cannot see any transverse motion. But okay, this is the simulation. So this is the numerical simulation. You can see almost only the x direction, longitudinal direction motion, and a traveling mode created out here, and the energy becomes smaller and smaller because of the time. Yes. The other experiment, a numerical experiment. Okay. This is the case when you change the amplitude much more high. So you can see Y directional motion, transverse motion, but the energy can be localized. Not so much. Yeah, this is a localization. I guess that this is very similar to this experiment. So then this is now the newest one, and now I will discuss what happened in this system and so on. Okay. Thank you very much for your kind attention. This is my introduction of the experimental one. Thank you.
So is there any questions?
I have just a simple question to show this nice setups and other things. Do you have some potential applications in mind for your experiments? In industry maybe or somewhere?
Industrial, this is a very good question, but it is, well, controlling the nonlinear excitation in a localized mode is probably can be utilized for controlling the heat flow in a material or something like this. But it is large system. We can only discuss on the basic characteristics of nonlinear localized mode. Actually, I don't have no idea to make this type of experimental system use engineering field. But it is just a toy model to investigate the basic characteristics of interesting nonlinear phenomenon.
Yeah, so question regarding the stability of this nonlinear excitation. So you, in previous slides, you keep on exciting the initial point. So what if you just excite it once and let it evolve? Will you see, or it will damp so quickly that you will not be able to observe that?
So please repeat one more time.
So let's say you start with a single initial condition at once and let it evolve. Then you will also see this excitation moving. If you here you are continuously exciting the system, right? I'm saying that if you excite it once and let it basically evolve, will you see, or it will die quickly? So that's why you are exciting it.
Yeah, if you maybe pick one by hand, you can observe traveling wave from here to there. Okay. Shock wave can reach from the end to end. Yeah.
But it's not a shock wave, right? It's slower than the group velocity of.
I think so.
Questions? I also have a question. So, are you thinking of expanding your experiments to a second dimension? Because at least there are some interesting system of flat bands with ladder-like structure, just two lines of interactions.
Yes.
Or also there are, for instance, we are also thinking of some fractal structures, but it of course reflects some big fields of interacting oscillators.
Yeah, in this slide I don't have an example, but this is very easy to change the position of each oscillator, and we have tried the 3 lines of oscillators, but and then we are going to investigate the stability of the moving grid, the difference between this straight line or 3 lines. But you mean, as you may know, the 2D the oscillator makes a number of oscillators become n square, and it's very difficult to do in the experiment. So I guess it is not so feasible for
you. What is the maximum amount of oscillators you can have?
It depends on my free time. But this time I have 20 or maybe 31, and if I have time, maybe 100 is okay. But 100, but 10 by 10, I don't think it's enough for. But if I could, I can try.
What's first, Aniket?
So one is related to the comment that someone was saying, is that, let's say here, all the experiments that you showed were with open boundary condition.
Oh, yes.
So if you could maybe put them on a circle somehow and then excite just one side, then maybe this will keep seeing this breather moving round and round.
Yes.
And then second question is that I think you already mentioned that the base of these magnetic stretchy things, I don't know what these are, they are not fixed, right? Or they are like, yeah.
But fixed, I mean,
Are they welded or like, they can move somewhat?
yes, because this is just on a neodymium magnet, and
Okay.
it is very strong, but you can change.
Take it off and
Take it off.
put it somewhere.
Yes, but this oscillation doesn't change the position of the photon. Yes.
There is not much interesting thing coming from this motion of the bases because like you can have synchronizations and stuff like this.
But it's not moving. I mean, it's fixed. You can change it, but during these tests, these experiments, it is fixed.
Yes.
But you could arrange, so to say, a one-dimensional system with maybe two bands, two phonon bands, and then you could actually make maybe a flat band system in 1D, and then you can try to show whether these, because then these systems support compact localized tests, perhaps, and then you can check whether you can get compact ILMs, because under some circumstances you can continue them into by adding nonlinear terms, and you can see maybe that they stay practically compact. That's, I think, what Sergei Konyakin was mentioning, but you don't need 2D for that. You can actually work still in kind of like 1D, but you just have to arrange them in some clever way.
Another question? Thank you.
Oh, yes. I was wondering, do you do this by hand, like making by hand, or do you need to use some fine machinery?
For this month?
Yeah, or anything.
Yeah, I have. But I created on some scale, by using 3D printer, and I use like many all is. I don't have any pictures in this here, but I used some scale and put and adjust by my hand, and I look at this straight line and also something check, and then and also I check the waveform of traveling mode, traveling a phonon. So then, if the motion is very fine, you can see this is very nice motion. It is, I cannot see any defect or irregular motion in this system, and then maybe arrangement is okay for this purpose of experiment. No, I don't have any idea how to arrange in mechanical.
So I wonder how sensitive it would be to having these like irregularities, because in quantum systems this is the difference between integrable and non-integrable systems. They can be different at large scales. But probably yours is always non-integrable, I guess.
Yeah, I think so.
Any more questions? So let's thanks again the speaker. And so here is in the session. I take the opportunity, as you already know, that I'm leaving very soon, to thank Sergei for accepting my invitation to come here, and to all of you, because I'm really feeling here at home, and so one quality and so many interesting talks. So thank you very much to all of you, and we have a drink now.